Welcome everyone to the one day one problem the series. So since the past 1 month I had not been doing any videos on this particular segment. Reason is I was busy in showcasing the designing the website, and we had, as you all already are aware, that we also started with something like AS and A level videos. Okay, so with this, now let us start with this one. So this week, whole from December 2nd to December 5th, so 2nd, 3rd, 4th, 5th, 6th until 6th, we will be continuing with something on data analysis. This will be a common one for both IB1 and IB2. Okay, so next week I plan to do with SHM and circular motion, and after that maybe I would start with rotation and so on. So we will herewith not have separate series for IB1 and IB2 as much as possible, because I have to do with the other works also. I'll be giving the common ones. Okay, now let us begin with this. So mechanics, we have already done sufficient number of problems, so I will not be doing much of mechanics problems or kinematics and forces. We'll be only focusing on this. Okay, so this particular problem on data analysis, it's very important. The reason is because, you know, in paper 1 for 2025 first assessment paper in IB, so 20 marks have been allotted for the data analysis in HL, and the rest of them 35 marks is for the paper 1, that is 30 marks is for the paper 1, which is for the what you call MCQs. Okay, as a result of this, so this I feel it's very important to understand. So if you have any questions, any doubts in not understanding this one, you can always message me or you can ask me in the class. Okay, let us begin with this now. So this question is for 8 marks, so I have allotted 8 minutes for this one. Let me begin with this question. Right, a student investigates the oscillations of a horizontal rod hanging at the end of a vertical string. Okay, you have a rod, you have a vertical string over here. From the view over, the student starts the rod oscillating and measures the largest displacement for each cycle. Okay, so it oscillates like this. Okay, so therefore he finds out what is this, where the amplitude. The student begins to take measurements a few seconds after releasing the rod. Okay, so he waits for sometimes, as if suppose it is a rod, it keeps on oscillating like this. He waits for some time. Okay, the graph shows the variation of displacement x with time since the release of the rod. The uncertainty for t is negligible. Okay, so error bars are drawn along the x-axis. This is t over here. What kind of graph is this? You see, it is now decreasing in an exponential way. I do not know whether it is inversely proportional or not. Anyway, let us read the problem to understand further. On the graph above, draw the line of best fit for the data. Whenever the data is given and whenever a graph is given, the first thing we expect is draw the line of best fit. So how do we draw the line of best fit? We start with this. Okay, let me take this. We start with these dots over here and see to it that I draw a curve. Remember, line of best fit doesn't always mean that it should be a line, straight line. It could also be a curve such that it joins all these points over here. So therefore, now let me take up these points. It should be a smooth curve. Right, I've drawn some curve over here. Okay, now next, in fact it should be able to go through all these central points over here, but I have drawn it like this over here because I'm not able to do it using my pen over here. Okay, next, calculate the percentage uncertainty for the displacement when t equal to 40 seconds. Percentage uncertainty for the displacement when t equal to 40 seconds. At t equal to 40 seconds, what is the displacement here? This is the value here. Okay, now let us understand what does each small square box represent. Okay, so now let us say, for example, if I take 2 here, the next box here will be 4 here. In between them, how many boxes are there? 1, 2, 3, 4, 5. 5 boxes, which means each box should represent 2.4, 2.8, 3.2, 3.6. Okay, along the y-axis we understood the scale. The first thing which we need to do. Then along the x-axis, it's quite easier. 0 to 5, 5 boxes. That means each box will be 1, 2, 3, 4, 5. Okay. Now let us start with t equal to 40. At t equal to 40, if you notice this is your 2 here, this is your 2 here, and this is your 4 here. This is your 4 here. And where is this box here? This is a 2, 2.4, 2.8, 3.2, 2.8 to 3.2. Maybe it's at the midpoint. So I can consider this as to be 3, right? So therefore your x value is equal to 3. And what is your delta x? Delta x is nothing but this small box that I have. Let me zoom into to showcase what is that value here. So if it is this one, let me rub this off. Now as a result of this, if you look at this, this is your 4, this is your 3.6, this is your 3.2. So this is my 3.2, and this is my how much is this? This is 2.8, and this is your 2.6. This is your 2.6. If this is 2.6, this could be somewhere around 2.7, for example. This could be 2.7. And if you look at this one here, this could be 3.2, this could be 3.6, this could be around 3.5, right? So therefore, now the difference here, what is this midpoint here? This is 3 here. This is 3, this is 3.5. So definitely this distance should be 0.5. Okay, this is your delta x. Let me reduce this. So therefore delta x is equal to 0.5. Now what we do is, what is he asking? Percentage uncertainty for displacement. So delta x by x multiplied by 100 is equal to how much? What is delta x now? Let us go back to the graph. I got 0.5 and x equal to 3. So I'll substitute these values and I'll write 0.5 by 3 multiplied by 100. So what is the value? Let me take my calculator. Right. Okay. So now towards it, 0.5 divided by 3 will be equal to so much, multiplied by 100 should be around 16.67. Okay. So this should be 16.67. So answer is 16.7%. Okay. The student hypothesizes that the relationship between x and t is x equal to a by t. What does it say? It's a inverse relationship, where a is a constant. To test the hypothesis, the x is plotted against 1 by t as shown in the graph. Okay, so here it is x, this is 1 by t. Okay, now you see, do you think the hypothesis is true? No, see here. So it is going straight like this until here, and after this it takes a curve here. Okay, so the x versus 1 by t, x is not proportional to 1 by t here. That's what we can understand. Okay, now let us understand the question. The data corresponding to point t equal to 15 seconds is not being plotted. Plot this point on the graph above. Okay, t equal to 15 seconds. Array, if I now find t equal to 15 seconds, here I'm not able to find, because you get only 0.25. What is wrong? Which means t equal to 15 seconds is not there. Should I say the question is incorrect? No, question is not correct. It's not incorrect. It's actually correct, because the plot here is 1 by t here. It's 1 by t. Okay, you should always note this, 1 by t. So which means if he is asking for t equal to 15 seconds, find out what is the value for 1 by t. What is 1 by t? Let us find out that value. So that value would be 1 divided by 15, should be 0.06. 0.06. Now do we have the 0.06 here? Of course we have this, right? 0.05 you have, 0.10 you have, 0.06 should be somewhere here. Now let us see where is 0.06. See here, how many divisions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 divisions, which means 0.5 second per second is divided into 10. So this could be 0.06, 0.05, 0.055, 0.06, and so on. Okay. Now what is he asking here? So plot the graph above. So you need to plot the value here. Now when I put x equal to so much, sorry, when you get 1 by t equal to so much, what's the value of x? The value of x is not given. How do I find the value of x? Is it given here? For t is equal to 15 seconds. For t equal to 15 seconds, the x value was seen to be, this is 8, this is 8.4, 8.8, this was 9. This was 9 here. So you should get the value of t is equal to, at t equal to 0.06, the x value was seen to be 9 centimeter. So I need to plot a graph there. 0.06, the value of x is equal to 9. Where is 9 here? This is 8. This is 8.4, 8.8, 9 over here. So this should be at this point. Okay. So it should be at this point, and then no need of any error bars. So we have drawn. Okay. Now let us start with the second question. Next question. So such is a range of values of t for which the hypothesis may be assumed to be correct. Okay. So I already told you this cannot be true for every value of t. Okay. So therefore now you see, where is the straight line here? Okay. Let me take up this. The straight line is observed to be, so if I draw a line here, start from here, observed to be from here to, I can draw until maybe until here, and after this you see it changes, right? It changes here. After this It changes, see, it changes over here. So therefore, maybe it is valid only from this value. For 1 by t value is equal to how much? This is 0.025 to it goes until here. See this point, there's no point over here. You cannot consider this. So you have to take this line, this line would be equal to 0.04. So for 1 by t values lying between 0.025 to 0.04, this hypothesis is correct. Okay, don't take this region, don't take this as 0.05 over here, which will be incorrect. Okay, in other words, for the values of t, this should be, now what is the value of 0.1 by 0.025? Let us find out this value. This is 1 divided by 0.025 is equal to 40. 40 here. 1 by 0.04, what is that value? 1 divided by 0.04 is equal to 25. 25, which means this hypothesis is true only for the values of 25 to 40. For values of t lying between 25 to 40. For the rest of the values, it is not true. So you just need to write the values of, for the values of 1 by t, this is being true for 0. What is it value we said? 0.025 to 0.04, 0.025 to 0.04. Okay, this will carry 1 mark. And for the values of t, this is seen to be true for 25 to 40. Okay, so this ends this question. Okay, tomorrow we will see the next question.